start on this computer.
There you go.
All right, just give me a moment. Is this all right? You can see my screen, everyone?
Yep.
Okay, and can you hear me okay? If you can't, I will increase the volume.
Yeah, you're fine.
Okay, excellent. Thank you, Natasha, for the introduction. I'm really happy to be talking about this work and this paper. I thought it was really exciting and something new to try. SGD was not in my wheelhouse when I was finishing up my PhD. I was actually working on silica sinks and a reverse weathering sink. But then Joe and I were finishing up at the same time, and he had all of these samples, and he was just like, why don't we just run them and see what we get? So we did, and we started to see some really interesting data. So I need to acknowledge straight away I'll be presenting data from this main paper, and my co-authors were Joe Tamborski, Matt Charette, and Kirk Cochran. Joe is now at the Old Dominion University, and after doing a postdoc with Alan Schiller, I'm now at the University of Colorado at Boulder. And I sit in both INSTAR, which is the Institute of Arctic and Alpine Research, and the Department of Geological Sciences at CU Boulder. So I want to spend a couple of slides talking about the importance of the reactive silica cycle.
Shaily, can I stop you?
Yes.
I think your screen is showing some leftovers from the Zoom settings. Can you just get out of sharing your screen and do it again? Maybe that would...
Okay.
Oh, let's see. You have to click on... Okay, can you try it again?
Okay. Let me see. Share screen. Okay.
It could have been just my screen. I don't know.
Is this okay?
Yes, perfect.
Okay. So as I was mentioning, I want to start by talking about the importance of the reactive silica cycle on the surface of our planet and how it's coupled to the biogeochemical cycles of a host of other elements. This shouldn't be a surprise. Silicon is the second most abundant element in our crust. But I want to talk specifically about the controls of silicate mineral weathering over atmospheric CO2, how it's an essential nutrient for many phytoplankton, how it also acts as ballast material. So this is a part of the biological portion of the carbon pump, and how it sinks in the ocean are one of the major reasons why we don't have runaway soda lake type oceans. Why this is a major control of alkalinity, cations, anions, and trace elements, many of which are being vetted as proxies for silicate weathering and reverse weathering, and how those processes control atmospheric CO2 in global climate. So for example, this is a model or a time scale of silicate weathering, the negative feedback of silicate mineral weathering on atmospheric CO2. Here you've got silicate mineral weathering right up here, and the amount of carbon it's purported to draw down. And you can see there's volcanism and carbonate weathering. There's burial as a calcium carbonate in the deep sea. But you can also see that there are some big avenues that are missing, like SGD. And I'm not sure, I'm going to spend a little bit of time talking about this too, because we found that when we were trying to get this data published, that we got a lot of pushback from the oceanographic community. And I wondered whether it was just simply how we were teaching our models of global cycles or what have you. You're using these box models, and I noticed that in my classes, we didn't talk about the sides of those models as being porous or having any fluid flow or reactivity. So, I think this starts pretty early on, and it propagates. So there are considerable efforts now being placed on, I think, coupling the silica and carbon models and trying to back calculate how they co-varied almost through the last 4 to 5 billion years of, well, not 5 billion, but 4 billion years of Earth's history. So I think this is really important. So, okay, you have silicate mineral weathering on land. It takes up atmospheric CO2, and the end products that gets delivered to the ocean via streams is your alkalinity and dissolved silica, along with a host of other elements that may have been in that parent rock. And once it's in the ocean, silicic acid, or a protonated form of silicic acid, monomer or polymer, silicifiers like diatoms, for example, or radiolaria will take this up and precipitate this amorphous opal phase. Now, diatoms alone are responsible for about 15 to 18% of global primary production. And silica is an essential nutrient for them. They need to have it in order to complete their cell cycle. And so this is yet another way that the carbon and silicon cycle are coupled in the ocean. And another way that they're coupled, and I'm arguing that we should start thinking about them in these coupled terms, is that it acts as ballast material. So when you're looking at the sequestration of organic carbon from the surface to the deep ocean, the primary phase that carries that carbon down to the seabed appears to be opal, and that makes sense. They're essentially precipitating this amorphous glass. Glass is denser than water, it's going to sink. So this is yet another way that the silicon and carbon cycles are coupled. And finally, once it does reach the seabed, you can have a series of reactions, generally termed reverse weathering reactions. And this is the formation of aluminosilicate phases at the sediment water interface. And the formation of these phases are going to impact your element budgets of your major components of seawater, like chemical constituents of seawater, like potassium, magnesium, and also alkalinity. Now, if you recall, your pH and your alkalinity of the ocean is what's also going to control the diffusion of CO2 into the ocean from the atmosphere. And recall that the ocean is the biggest sink for atmospheric CO2 on our planet right now. So this generalized reaction right here, reverse weathering reaction, was proposed in the 60s as a way of balancing the element budgets of dissolved constituents in the ocean. And again, as a way of explaining why don't we have these runaway alkaline oceans. So this project started as a study of Long Island Sound. So at the time, Joe Tamborski was working on a radium radon mass budget for this part of Long Island Sound. And he was also looking at nutrient fluxes, specifically nitrogen. And at the same time, I was finishing up my project on using a cosmogenic radionuclide of silicon 32, to constrain how much biogenic silica was actually stored in sediment. And I was noticing here Long Island Sound, what the estimate here is like 13% of biogenic silica is stored in sediment. This is quite different from previous estimates. It's almost a threefold increase. And what I was noticing already is that something wasn't making sense when looking at just the regional mass balance of dissolved silica inputs and outputs in Long Island Sound. So the major input is the Connecticut River for the river supply. And I was just noticing that the amount of dissolved silica that was being supplied by the river couldn't balance the amount of biogenic silica, on the sink side, of how much I was seeing was being actually taken out of the water column. Like it seemed to equal or exceed the river supply. So it's like something, I'm curious of delving deeper into this. And so Joe had these samples and we started looking at them. So my interest in this was that I wanted to figure out this mass budget or this mass balance on a local scale. And then we started chatting with Henry Buchanevitz, who's on this call, and Kirk Cochran was managing the both of us. And he got us in touch with Matt Charette. And Matt Charette sent us some Woolcoit Bay samples, along with data from 7 or 8 other endmember lithologies. And then we started to see that we perhaps had a bigger project on our hands than we initially envisioned, because we started to see similar trends across a lot of these data sets. And so then we started looking into the literature, and oh boy, the more we looked, the more we found. So that was pretty fun. So let me take you through what we found. So initially, this is one of those global mass summaries or budget summaries that I mentioned about the marine silica cycle. So this is from a summary mainly from Tregor and De La Rocha from 2013, and also Frings et al. From 2016. All of the units, the major flux units, are in teramoles per year. Teramole is 10 to the 12th moles. And you can see that in this mass budget here on the left, terrestrial SGD was estimated to be about 0.7 teramoles of dissolved silica input to the ocean at any given time. And if you're looking at the flux of these other inputs and outputs, you can see that it's really a minor component. Well, how is this estimated? Well, at that time when we started working on this, Patrick Frings in his paper had the best estimate. And what did he do? He took a survey of dissolved silica concentrations in USGS wells, inland wells, averaged them, and multiplied them by what he thought was a conservative volumetric freshwater flux. And that is how he arrived at this 0.7 teramoles per year of DSI input. So we thought, well, can we constrain this flux, but using only data from coastal aquifers that actually discharge to the ocean? Because what he was doing was this interior survey and a mass average of, I'm not sure, I think over 1,200 data points. And so we wanted to focus in on only coastal and subterranean aquifers that were discharging to the ocean. Excuse me, I have a little cough. So let me just remind you, I know a lot of you work with SGD, so this is not going to be new. And I'll go through this quickly, but there are several physical drivers of terrestrial and marine SGD. Terrestrial forcing is usually water table elevation or density gradients. And with marine forcing, it's tides and waves will force fluid flow through a subterranean estuary, or you'll have thermal gradients or sea level rise or fall that will impact your fluid flux. And rivers supply about 40,000 cubic kilometers per year of water to the ocean. Terrestrial SGD supplies about 2,400 cubic kilometers per year. The current estimate, one of the estimates for marine SGD is about 120,000 cubic kilometers of water per year. So just off the bat, when I talk about total SGD, I mean terrestrial plus marine. And I want to remind you, though you all may not need reminding, that a lot of the reactions that occur in mixing zones in surface estuaries also occur in subterranean estuaries. However, in subterranean estuaries, there's typically a higher sediment to water ratio. So that surface area to volume ratio is typically higher. And so a key concept in this talk for interpreting the behavior is a simple conservative mixing line. So to refresh, if mixing is going to occur typically with no non-conservative source or sink, you should get a straight line between your fresh and your marine endmember. However, if you see mixing curves that dip below that conservative line, you know that conservative mixing line, excuse me, you know that you have a non-conservative sink of that element. And typically, if you see something above the line, there's a non-conservative source of mixing. And if you use any form of stable isotope work or anything like that, that's another way of confirming whether you have conservative or non-conservative sources and sinks along this salinity gradient. So the other key difference between surface and subterranean estuaries is that typically there are longer residence times of that parcel of water. So that parcel of water sees or interacts with the surface of that material for longer than it would in a surface estuary. So we compiled initially this groundwater data, and it was collected from coastal aquifers with contrasting hydrogeology across this freshwater saltwater continuum. And we supplemented the data of the initial Long Island Sound data with new data from these different locations. And then we began compiling dissolved silica data from the literature. So we compiled data from about 50 coastal SGD studies, and we focused again on shallow aquifers. So we were only looking at data that was taken in less than 50 meters depth. And again, these are all coastal aquifers. So these are the new data that went into that paper. And let me just take you through a couple of these plots. But first, the filled in circles are the surface water concentrations of dissolved silicon. And on the bottom, on the x-axis, you have salinity. And on the y-axis, you have dissolved silica concentration. And the open circles are your groundwater circles. The triangles are estuarine circles, estuarine samples. And then you've got seeps and cenotes that form a minor fraction of these samples. So when you look at an endmember like Guam, which is a carbonate lithological endmember, you typically see conservative mixing, and you see DSI concentrations of about, in the freshwater endmember, of about 18 micromole here. Now, if you move on to something that has a more complicated lithology, like a glacial till, it's very clear that you see a non-conservative source of dissolved silica, and that these concentration distributions can't be explained by a simple mixing model between a fresh and a marine source, or terrestrial and a marine source. Similarly, for Mauritius, this is the conservative mixing line. You also see clear evidence of a non-conservative source that is elevating your dissolved silica concentrations above what you would expect. So we thought, okay, well, how do we calculate a global supply of this source to the ocean? And we use this coupled lithology hydrology model. So the lithology is taken from Gibbs and Kumpf, and the freshwater, the water fluxes, are taken from Zexter, 2007. And the size of the arrows is the intensity of your terrestrial SGD flux. Now, there are more complicated models out there. I think Nils is on this talk. I think he's done a lot of that more complicated modeling. But we thought that given that we were seeing that we had such a limited, I think these are still limited data sets, because we haven't looked at in a big way or a lot across many different studies, like seasonal cycling of dissolved silica concentrations in the subterranean estuaries. We thought that the errors in this model were good enough to encapsulate seasonal cycles and benthic diatom production or primary productivity and things like that. So we were comfortable with the errors in this model. So we coupled this with our data compilation, and this is a summary of the locations that we used in our data compilation, and they're color coded by the endmember lithologies in that model. And they're just 6 endmember lithologies: igneous shield, carbonate sandstone, complex, and then shield granite. Now, the closed circles are the data that we found from the literature, and the open circles are the new 7 to 9 data sets that we added to the global compilation. So the open circles are from our studies. We also use this estimate of this total SGD based on an observationally constrained radium isotope model. And this is summarized in Kwan et al. 2014 and Charette et al. 2015. And so this inverse model quantifies the total coastal radium-228 source, which is then used to calculate your volumetric flux. And so the fluid flux due to SGD, total SGD, is about 12 plus or minus 3 times 10 to the 13 cubic meters per year. And if you see increasing radium-228 inputs with increasing dissolved silica inputs in pore waters, that indicates an input of mineral dissolution. And for those of you, I'm not sure if any of you on this call have not used radium-228, but if there is someone who hasn't used radium, it will desorb from your mineral surface if it encounters seawater. So if you're looking at quantifying your radium-228 or any of your other radium isotopes in a coastal sample, that's an indicator of marine SGD. So we're separating these calculations of terrestrial and marine SGD inputs. And in the terrestrial SGD input, taking an average dissolved silicon endmember concentration for each of those 6 different lithologies. And we're using that combined hydrogeological model. We're applying those averages to those coastal zones. And so what we see, this is a box and whisker plot of all of the different concentrations that we saw or we compiled in our paper of those 50 plus studies. And you can see that, as you would expect, maybe carbonate endmember has a low dissolved silica endmember concentration. It's a carbonate platform. And contrasted with the igneous extrusive, which the host rock has high silicon in it, you see quite a large spread and enrichment of DSI over what you would expect in a carbonate subterranean estuary. So we use that with that coupled hydrogeological model, and you can see the model is available in our paper. So if you go to the appendices in that paper, you can see the model. It should have all the links that are active in it. So we use simple error propagation there. So if you have a project where you think you've got a lot of data from these endmember lithologies and you expect mineral dissolution to contribute to SGD, you can start putting in your endmember concentrations in that model, and it'll start calculating. It'll calculate something for you if you just put it in that table at the top. So it's there for your use if you would like to get a first order approximation of your SGD flux and then see if it's worth pursuing. Of course, it's worth pursuing. There are not enough SGD studies in the literature. So yes, please pursue. So the terrestrial SGD input of dissolved silicon, and this is back in the time, I just have to make a point, where we're using capital D, and I think that we should use lowercase d because capital D could be confused with deuterium, and we're not talking about hydrogen silicon, we're just talking about dissolved silicon. So that input we calculated to be about 0.7 plus or minus 0.2 teramoles per year. This is similar to what Frings et al. Got in his 2016 paper. However, I would argue that this is more conceptually sound because we're actually using coastal aquifers, plus we've constrained the error as well. Whereas in the previous paper, it was 0.7 plus or minus 0.7. Okay, so that's how we did the terrestrial SGD calculation. Now for marine SGD, what we tried to do, what we started doing, is that we determined that non-conservative enrichment for each lithological classification. And so we took the dissolved silicon concentration in the samples that had a salinity close to whatever was in your surface water, and we subtracted that surface water concentration from that average as well to be conservative. And at that time, while we were writing this paper, Cho et al. Also came up with an estimate of total DSI flux. So we calculated the marine SGD end member in a number of ways and ultimately decided that it would just be most scientifically sound to subtract our terrestrial SGD from their total input to derive the marine SGD end member. However, I'm going to go through a couple of other calculations that show that it's sound. So here is the spread of the data in our marine SGD samples. And we chose to only use these three end members because the shield granite, shale, sandstone, they just didn't have enough studies to corroborate any of this enrichment or lack of enrichment, as you can see with the carbonate end member. But the igneous extrusive and the complex lithologies did. So for example, I think in the shield, there are only 1 or 2 studies. So we decided not to even use it in our initial calculations. So this is what we arrived at for marine SGD dissolved silicon input, about 3 teramoles per year compared to 0.7. Now, if you remember that model at all, or if you work with the marine silica cycle at all, like the global silica cycle, the riverine input is about 6 teramoles per year. Whereas the combined total SGD dissolved silicon input is close to 4. This was huge for us because this is like you're corroborating that submarine groundwater discharge inputs are the second largest source of dissolved silicon to the ocean. And I want to remind you that we constrained our study only to shallow coastal zone, like the proximal coastal zone, only in 50 meters water depth. We did not look at deeper flow paths. So this was a huge revelation for me, for us. We were like, this is going to change things up a lot. But first, we needed to go through some calculations. Are these values realistic? Can they be supported with any other data? So, okay. We supported our data by looking at silicate dissolution experiments. And these are, a lot of these experiments occur with like volcanic glass or cleaned quartz fragments. And if you look at some of these results, and we used Tesher et al. Because they actually used different ionic strength fluids for their leaching experiments. So if we assume a residence time of about 1 to 7 days using their dissolution rates, we calculate a global SGD DSI flux of 0.1 to 1.2 teramoles per year. Okay, so we're in the same order of magnitude. That's not bad. What else can we do? Okay, there are also dissolution rate experiments of sands in static and flow through incubation. So these are natural samples that we're using. For example, there's this paper by Pierre and Schutz in 2009, where he's looking at these tidal sands as reactors. So what they found was that, okay, this is the seawater at the shoreline, and these are samples along the beach. So you're going inland here if you're going to the right, your dissolved silicon concentration. So the seawater salinity at the shoreline was 34. In pore waters, it's also 34, but you can, I think, clearly see that you have enrichment of dissolved silicon in just these tidal sands. And I believe he completed this project with like a plastic bucket and a toy shovel. So you can do science anywhere, and you should do science anywhere, unless maybe you're on vacation. And even then. Okay, so moving along. So he took some of those sands, or they took some of those sands, and they did these static and flow through incubations of the static incubation didn't have water flowing through it. The flow through incubation did have water flowing through a plug of sand. And they were tracking the dissolved silicon concentration in the fluid at different water to rock ratios. And what they noticed that after about 3 days, they had this initial sharp increase, or this, that the rate of increase changed after 3 days. So initially it was faster from 0 to 3 days. And then it kind of started plateauing off and tapering off. And this is also consistent with dissolution rate experiments of volcanic glass and synthetic materials. You have this initial release or dissolution of that solid phase, and then that dissolution rate decreases, which suggests that something is slowing down that dissolution reaction. Likely it's reaching some sort of equilibrium. The other option is also that you're reprecipitating some of that dissolved silicon that's in solution, and you're capturing it again into another solid phase, which is also consistent with these studies of dissolution rates using synthetic material. This has been, these types of static and flow through experiments have been recreated in other locations and with other types of endmember lithologies or sands. This is one from the Mediterranean Sea. And again, you also see this initial sharp increase in this incubation of this beach sand at different water to rock ratios or surface area ratios. So you see this initial rapid dissolution of the silica, the silicate mineral surface. And then you'll see a tapering off, which suggests either something is impeding that dissolution reaction or that you actually have dissolution and precipitation happening at the same time. So how can we tell? Well, we'll get to that. So compiling these dissolution rates that we saw in the literature with a range of marine SGD values for a particular endmember lithology, we arrive at an estimate of DSI inputs from marine SGD for a particular residence time. The residence time changed from 1 to 7 or 7 to 28. And the marine SGD inputs on a global scale, the rates that we got were about range from 0.04 to 1.2. So again, I don't think that's bad. We were trying to be very conservative with what we were estimating. And we wanted to see whether mineral dissolution can support these dissolved silicon concentrations. Because as we were presenting this data to the oceanographic community, some of the pushback that we would get is that, well, actually what you're seeing is the dissolution of those biogenic frustules. You're actually not seeing lithogenic dissolution. And the difference there is that if it's just dissolution of biogenic silica, that's a recycled flux. That's not a net input. And so that was the pushback that we were getting. So a lot of this other data that I'm going to show you for the rest of this talk was spurred on by those, I'm just checking my time, that feedback that we were getting from the oceanographic community. Okay, I summarized this. This is a summary. So if you have a residence time of about 7 to 28 days with these dissolution rates that you see in these incubated sands, you get an equivalent global flux, an estimate of 0.2 to 1.4 teramoles per year. Summary of these studies. So a third way, that's not bad, similar order of magnitude, that's not bad. We're zoning in, maybe on a correct answer, or our answer is not wrong. based on these experiments. Another thing that we did was these back of the envelope calculations. So we looked at the dissolved silicon enrichment in these different end members. So the carbonate end member did not have any enrichment in the marine SGD portion, but the igneous, extrusive igneous and the complex lithology aquifers did. They had about a 50 micromolar enrichment in that marine SGD end member. And we took an average of these, which is about 20 micromolar, a flux weighted average, and just multiplied it by a global volumetric SGD flux and got about 2.5 teramoles of DSI per year, which is pretty darn good, I think, to the estimates that have been gotten or derived from all of these different methods. And we did, plus minus, okay, let's take half of the total volumetric flux. Let's take the max, the 120,000 cubic kilometers per year. And you get somewhere between 2 to 4 teramoles per year of dissolved silicon inputs via SGD. You could take that coupled hydrogeology model, which only has the terrestrial input, and multiply each of those fluxes 3 to 4 times, just to see if you get a first order estimate of what your total SGD would be. It's about 3.5 teramoles per year of dissolved silicon inputs using that model. So we now have, in my mind, this is converging on the correct answer, or this is very close to the correct answer. We've now done these calculations a number of different ways. And to sum up the paper, we see that terrestrial SGD contributions of dissolved silicon are the highest in the Pacific Ocean and in the Mediterranean. And generally on a global scale, we estimate that submarine groundwater discharge supplies a little over 50% of the total riverine inputs. It's the second largest source of dissolved silicon to the ocean. So if we go back to this conceptual model, or the summary of this conceptual model, total inputs of dissolved silicon to the global ocean just from SGD puts the total inputs at 25 to 30% higher than prior estimates. What does this mean? This lowers the estimate of residence time of dissolved silicon from somewhere that's about 10,000 years to somewhere that's closer to about 7,000 years. This is not how this element has been modeled in global climate models. This goes to considerations of what nutrients are limiting when you're looking at primary production, because now you're getting into residence times that are closer to nitrogen versus residence times that are closer to phosphorus. Phosphorus, I think, has a residence time of about 20,000 kiloyears. So this, I think, really changes the number of times that molecule of silicic acid, or that element of silicon, will go through all of these different cycles, and how fast the ocean chemistry can change just with respect to this one element. So our inputs managed to convince a lot of oceanographers that this is real. So this is a recent compilation from Tigger et al. 2021 of this global silica model. You can see right there on the left near rivers, got a SGD input right there of 3.1, which was took about 2 years of convincing, but they put it in based on all of these different lines of evidence. And I'm just summarizing some of them. There's more. There's this Fabre et al. Article about physical disturbance of sand and how physical wave action will also dissolve sand, and we just don't consider it. And guess what? They see enrichments of about 50 micromolar silicon, which is the enrichment that we saw in the igneous, extrusive, and the complex lithology. So I'm just summarizing some of the evidence. There's more. So I was curious, is there another way, like just to nail this down, is there another way to verify global SGD inputs and the accuracy of this summary? Because this has implications for climate models. And bear with me, I'm going to just take you through some stable silicon isotope data. So this is a compilation of stable silicon isotopes from 2018, Jill Sutton. On the bottom here, you have all of the different reservoirs of reactive silica. And in the middle with the bars, you see the range of stable silicon-30 isotope values. And just for now, just focus in on, it's complicated, but let me just point you to the groundwater section. Okay, so here's groundwater. It has a average isotopic value in this compilation of about 0.2 per mil, and the flux to the ocean is about 0.7 teramoles per year. So this is not taking into account the marine SGD endmember, total SGD. However, when we look at studies that are actually trying to characterize, and there are only two that I know of, this marine SGD endmember and the delta silicon 30 value. This is a study off of the coast of Germany from Ellert et al. 2016. So here are their study sites, and here are these pore water profiles, or these of dissolved silicon. Got a transition zone, a clay layer, salt water lying underneath. So what are the DSI value, or the delta silicon 30 values? They range from about 0.5 per mil to about 1.1 per mil. Now recall what was in that synthesis. The average, they were taking it as 0.2 per mil. So what does this mean? Okay, bulk silicate earth, if you're just dissolving primary silicate minerals, has a signature of about 0 per mil. And if you're dissolving a diatom frustule or a biogenic silica frustule, it has, at this location, an endmember value of about 1.9 per mil. So what this profile is telling us, along with other pieces of evidence that are in this paper, is that lithogenic dissolution alone and biogenic dissolution alone of the silica substrate cannot explain these pore water profiles. And they go on to do these mixing diagrams. So here is at the top in panel A, this is what the values you would expect if you were just dissolving a biogenic silica substrate. The bottom, this dashed line, is what you would expect if you were just dissolving mineral dissolution. The one in the middle is the mixing curve between seawater and groundwater. And you can see that these values of delta silicon 30 don't follow along any of those lines. And when you look at the other pieces of evidence that they use, which is uptake of potassium, of magnesium, and saturation indices of different clay minerals, what they're proposing happens in this mixing zone, the salinity gradient or the salinity front, these shallow estuaries, is that you have both lithogenic mineral dissolution and you have a reverse weathering type or an authigenic aluminosilicate precipitation. Like those are the two reactions that need to happen in order to explain these stable silicon isotope values, which I think is brilliant and really cool application of this tool. So again, to summarize, biogenic silica dissolution can explain the data. Mineral dissolution alone can explain the data. What you have instead in the subterranean estuary is both dissolution and precipitation. And in the same subterranean estuary that they were studying, this is from Oler et al. 2019. When you see concomitant release of dissolved silicon and radium, this is yet another piece of evidence to me that you can use if you're talking to someone who doesn't believe that SGD is important. And I've talked to a few of those people. But biogenic silica or dissolution of biogenic silica would not be explained. These profiles can't be explained by biogenic silica dissolution alone. I think this is yet another piece of evidence of this concomitant release of radium-224 and dissolved silicon that shows that you have lithogenic material that's dissolving in this mixing zone, and that this input is a real net input, not a recycling source. So these summaries of marine silica have evolved quite a bit over the last 4 decades. This is a simplification. And in initial summaries, it's mostly rivers and biogenic silica, riverine sources and biogenic silica sinks that were the important constituents in these summaries. And this is on the right is just a box model summary of Trigger et al. So again, I'm asking, is there a way of independently verifying this latest summary? And this is work that, bear with me, let me just take you through this, of marine silica cycle, where a collaborator and I have compiled, have worked on what Sutton et al. Did in 2018 and have compiled all of the measurements that we could find of stable silicon isotope values in any of these reactive pools, but only on the surface Earth. So we're not looking at any mantle values. And we're doing Monte Carlo simulations to see whether sources and sinks can be balanced. So those are sources, these are sinks, the main sinks are diatoms, radiolarian sponges, and there's a reverse weathering sink. Whether, so you don't pay so much attention to the numbers, but because they can get complicated. But one simple question we asked is that, can the stable silicon isotope budget be balanced using the Trigger et al. Model, using these isotopic values or these range of isotopic values? So using Monte Carlo simulations, we found that it could, that it was balanced. The marine silica budget can be balanced at about 14 to 15 teramoles of inputs versus outputs. I don't think I have much time, so I'm going to go through this quickly. One of our summaries is the majority of the Monte Carlo simulations showed that the latest Trigger et al. Summary achieves mass balance, which is one of the questions that I queried with this compilation effort. And we've done some other things with it, and I'm happy to talk to you about that later. But we seem to be multiple lines of evidence converging on a marine silica cycle model that is consistent across different studies, small scale and large scale. And just recall again that the silica and carbon cycles are coupled. And there have been recent modeling efforts to explicitly use those a coupled biogeochemical model to explain climate evolution, or to try and do these climate evolution studies, which really has been interesting. But so far, SGD has not played a big role in those models. And I want to emphasize again how important the low temperature geochemistry in the coastal zone is to the silica cycle. You've got amorphous silica inputs from rivers. You've got wave action that's perturbing these sands and likely dissolving some of this material, SGD flux, and this movement of water that modifies this material. You've got low temperature weathering of any material that escapes dissolution along the salinity gradient, settles to the seabed, the shallow seabed, and then continues to dissolve. And then you've got this interplay of reverse weathering and opal, which also, I think I need to put in another arrow here to make it clear that, okay, there's burial, but then there also seems to be reverse weathering occurring along these flow paths. And I'm going to call it reverse weathering because by definition, it needs to happen at a sediment water interface. And when you have an advective flow regime like this, I think you could model that as a sediment water interface. This has major implications for other budgets that are associated with silicate minerals like germanium. Germanium is being vetted as a potential proxy for silicate weathering. However, there's a big mass imbalance in the use of its isotopes, and even we just don't know where the sinks are. Similarly with lithium, there are efforts to use these records and project, okay, how warm was the Earth 60 million years ago? Here, let's try all of these different things. But if you look at these inputs and outputs in this paper from Lee and West, you've got riverine and hydrothermal inputs. You don't have any SGD inputs, but lithium is hosted in silicate minerals. And this leads to a mass imbalance when you look at its stable isotopes. The seawater has a signature or a value of 31 per mil. Rivers have an input value of about 23 per mil. There is a missing 8 per mil. There's an 8 per mil difference there and we don't know what the major sinks of lithium are. Okay, I only have a couple of minutes, so I want to suggest that a sink is in marine SGD from some preliminary data that I have of these lithium isotope records. I don't think I have time to go through this, other than to say that it seems like with marine SGD, along that flow path, you have consumption of dissolved lithium, which is not what I was expecting. I thought it would be a net release of lithium. You have consumption of lithium, and the end member leaves a little heavier than what came in. So this may be one of the missing sinks of lithium, which is different from, the net effect of this is different from what you see with dissolved silicon. So to summarize and conclude, the global dissolved silicon flux from SGD is about 50% of the global river flux. Basalt and complex lithologies typically exhibit a 10 to 20% enrichment in marine groundwater. The residence time of DSI right now from the trigger, I'll estimate, is about 6,000 years. So this will impact your climate models. And you have this really interesting interplay of dissolution and precipitation reactions in the subterranean estuary that I'm arguing should be modeled as a sediment water interface. And these have impacts to the stable silicon isotope budgets and budgets of other silicate mineral weathering products. And these initial results indicate that there's like this differential kinetic control on the behavior of each of these elements. That's likely dependent, again, on fluid flow and residence time, which will impact these dissolution and precipitation reactions. Before I end, I need to acknowledge all of the people who helped us get to this point: Christina Halburn, Bob Aller, Henry, hopefully he's still on the call, Megan Goni, Alexandra Rao, Henrietta Delova, and Paul Henderson. And I want to thank you for your attention.
Thank you, Shaily. This is very interesting and exciting. We really appreciate your time for coming and telling us this story. I'm really fascinated by the results and the fact that you guys set up silicon on the second largest source to the ocean after the rivers. And the impact on climate change was like silicon is enrichment, right? Yep.
Yep.
Do you guys have any questions? I'll turn it now to our participants. Yeah, we have a chat from Henry saying nice job. And yep, interesting stuff. Bill?
Yes, I had a quick question.
Mm-hmm.
I agree that was very interesting data and nicely presented also. So thank you for that. in your introduction, you mentioned concerning reverse weathering.
Mhm.
I think you were citing some work from Garrels and McKenzie.
That's correct.
And you mentioned that reverse weathering only goes on at the sediment water interface.
Mhm.
And I wondered, why did they restrict it to just that realm?
So the way that they defined reverse weathering and the way that I am using reverse weathering is a way of balancing budgets.
Mhm.
So I'm using this differently from what you may have also heard or read in the literature about authigenic clay formation. So all authigenic clay formation is a reverse weathering reaction, but not all reverse weather, sorry, the other way around.
Uh-huh.
The other way around. You can
Okay.
have authigenic clay formation at depth, but if that fluid is not interacting with seawater above it in any way, it's not going to impact your budget summaries of things like potassium, magnesium, or alkalinity. So you do see
Mhm.
conversion of smectite to illite, kaolinite at depth. But if that fluid is not interacting with the water column above it, then I see that as an internal conversion or an
Okay.
authigenic
Yeah.
clay formation reaction, but not a reverse weathering reaction.
Yeah, I
And it's
see.
terminology, but I'm using that terminology like as it's coined.
Mhm. Okay, good. Thank you.
I see Niels has his hand up. Niels?
Yes, I have. Thanks a lot for the talk and the work and the paper. It was fun to see then, and it was even better to get it presented like this now. I wonder about the carbonate aquifers, because you basically said they have zero DSI concentrations.
Zero
I didn't
enrichment.
know
Zero,
enrichment.
no
Yeah.
enrichment of dissolved silicon above what we saw in the surface
But
waters of the estuary.
I think they should have even enrichment, because often enough they're not pure carbonate, but there is shells in there, and these would be ancient shells then, and no one can really say, okay,
Yeah.
This is recycling. Yes, it's recycling, but on geological timescales.
Right, right. I agree with you there. I want to point out that when we were writing this paper, we wanted to be as conservative as possible.
Yeah, don't worry. I'm not
So
criticizing you.
I think you are correct. I think
Oh.
that none of these are pure end members.
Yeah.
And there was that recent paper by Martin et al. 2020 and 2021, I think, from an aquifer in Australia. And they also saw a little bit of enrichment too, despite the main lithology being like a carbonate end member. So are you familiar with that paper? They present a lot of stable isotope data, which is fantastic.
I don't know it actually.
Oh, it's A.N. Martin,
Okay.
I think is the first author. I can
Okay.
send it to you as
That'd
well.
be
If you
cool.
can't find it.
I'll check it out. I should be able to find it in the end.
So they have both stable silicon and stable lithium isotope data that they present in the same samples. So
Okay.
I think those two studies are really, they're great.
Yeah.
And I'll
And
put
then-
my email in the chat.
Thank you. And regarding the discussion of the recycled flux, it's not a question, it's more a comment, because I often also encounter this kind of discussion, this isn't real, this is not an actual new flux. But in the end, if there was no marine SGD, that flux wouldn't be there, that recycling wouldn't happen to that degree, at least not. So even if it's recycling, it's the reduction of a sink. That might not be a source, but the reduction of a sink is net. Basically, it increases silicon. So
Right. I agree. And early on in this project, because again, SGD, this is something I stumbled on as I was ending my PhD and going around in circles. So I was using very deliberately and I think this is Matt's suggestion of using terrestrial and marine and not using even recycling, even though we know that it's a circulation cell, to keep that clear. But I think the other big difference, or to comment on how you also come across these challenges, is that a lot of data that people have of, oh, well, there's dissolution occurring maybe from a biogenic source here in this case specifically, those are all in muddy sediment. They're all diffusive fluxes. And so I point out, well, I'm talking about an advective flow path. This is like a hydrothermal vent fluid or weathering of basalt at depth, but it's still a challenge. And I think the suite of stable isotope tools that we have now they're going to be one of the nails that we can use very effectively to say, no, this is not biogenic. This is not anything else but lithogenic mineral dissolution.
Yeah, you're right. That's really also convincing too.
There's a question in the chat. Shaily, do you want to read it?
Oh yeah. Hi. Yes. Yes, it does. So this was something. So the question was, how did Trigger et al. Separate marine SGD from this low temperature? I'm going to call it low temperature mineral weathering, and that's, I think, how it's called in Trigger et al. So we're talking about time scale here. So in this is how I separated it in my mind. So when you're talking about a surface estuary, that mineral, those particles are encountering that salinity gradient maximum a couple of hours, maybe a day, before it falls out of solution or it falls through the water column. I'm a chemist by training, so I think of falling out of solution. Okay. And then you have mineral weathering that happens in the coastal zone, in the shelf, and then you have mineral weathering that also occurs in the deep ocean. So I think those two fluxes have been separate or talked about separately, but the two may have been combined at 1.9 teramoles per year, which is separate from a hydrothermal flux. Does that answer your question? So this will be like slower dissolution that will occur probably of less amorphous material that won't dissolve straight away as soon as it sees a more corrosive fluid. And that flux is about 1.9 teramoles per year. That's the estimate in Trigger et al. So they are separate.
Okay. Shaily, I was thinking about when you say that you had this pushback for the different mechanisms and whatnot. So if you step back and think in your budgets, what is your biggest concern? Which component of the budget is your biggest concern?
Well, rivers have been pretty well studied. We have constraints on over 60% of riverine fluxes for many elements. And that's pretty good. I mean, to think that almost 60% of all the rivers are gauged in some way. That's not much of a concern to me right now. We have pretty good estimates now of heat flux from hydrothermal vents. Of course, we don't have a whole lot of data from hydrothermal vents, but I think that the two biggest questions for me specifically is this low temperature mineral dissolution that Xiaoling just asked about, and also quantifying like a global reverse weathering flux for me. The estimates that I have are only from the proximal coastal zone, not the distal coastal zone, shelf, or open ocean. And there is now emerging evidence, like quite a lot of emerging evidence of those reactions occurring there. It should, if the diagenetic conditions are correct or primed, it should happen. So I think we just need the tools to look, be able to constrain like your sediment budget, like where is your, it's not just staying on the shelf. What is happening in the delta, foreset, bottom set, submarine canyon. So if we can start actually getting good sediment budgets for these inputs, or how mass moves from the shelf down slope, I think we can start constraining these fluxes, but those are really big tasks and really interesting tasks.
Okay. Any other questions? It's just 7 of us left. So Shaily, thank you again. And thank you everybody for tuning in. Bill, Niels, Amy,
Yeah.
Kristen, Juling. Thank you guys.
Thank
Appreciate
you very
it.
much.
Yeah, great talk. Thank you.
Thank you.
Thank
Yeah,
you.
absolutely.
And see you again.
Bye.
Bye.
Bye. Let's see.
Do you wanna
Natasha,
stop I'm here. Yeah.
Yeah.
Do you want to stop recording?
yes.